So I want to talk about single-use seals and a few ways of thinking about them. But really, what they are is really a concept. Really a way of building consensus applications. Things that need consensus and so on. And I want to go start with really why that matters, which is the usual question. What problem are we trying to solve? I can imagine if I have my cell phone and open up my mobile banking app, or if I had better clip art, probably a lightning app or something, or some other clever thing. Ultimately, what I want to do is make sure that what I see on my screen is the same as what you see on your screen. Really, we're trying to achieve consensus. We're trying to make sure that for a given state, everyone in possession of it will have the same thing. And why this tends not to work with traditional crypto, which doesn't actually solve this problem, is because signatures are just math. A signature you can always sign multiple times. Using one pub key, I can sign as many messages as I want. So, what isn't like this? Well, in shipping, we've got this idea of a anti-tamper single-use seal. Essentially what this means is I can have a shipping container. Suppose I'm in Canada and I'm sending it off to here in Lisbon, and I can go communicate with the guy in Lisbon and say, hey, when you get this container, there's going to be this seal on it, and it's going to have such and such a number, and when you get that container, verify that number matches. And the guarantee given here is that these physical seals, for any given number, there should only exist one in the world. They're not supposed to reuse numbers and so on. In practice, I'm sure that guarantee isn't exactly correct, but that's the idea at least. And of course, the other part of the guarantee being, well, it shouldn't be possible to manipulate the seal. I shouldn't be able to open it, pull the container open, change something, and close it again. We can take this concept and apply it digitally. Imagine if we had some kind of construct which supported these three operations. You can generate it, and when you generate it, it's associated with a pub key P, or pub key script, whatever crazy concept you have, but essentially some form of authentication. And you can close it over a message with a signature that validates that pub key, and that produces a witness, W. And finally, you have verify, which anyone can run, and I verify a given message with a given witness against a given seal. And if everything's correct, this should return true. Right? Now, this all sounds like a signature, but what if we had a property where you couldn't run close twice? What if this was a one-time deal? Well, the guarantee we're talking about is it's secure if there does not exist for two distinct messages, two witnesses that both pass verify. So essentially this is just like a pub key, but we have this guarantee that you can only sign once. Now, obviously you can't do this with math. This is a stateful thing, but let's assume for a moment that we did have this guarantee. What could we go build with it? Well, you could build a blockchain. And by blockchain, I just mean a chain of blocks. And the property you'd have here is, well, you've got the series of blocks. They're all associated with seal. And provided you start with the same genesis as me, you can go forward and validate witnesses, and validate the seals, and verify that whatever data you have is going to be the same data I have. You might be missing stuff at the end, but anything that you do have will be the same as what I have. And ultimately, that's what Bitcoin's trying to do in the first place. We have a blockchain, and we want to go agree on transactions in the blockchain. You can come up with other applications, like what if we have software releases? I don't want to have a different version. I don't want to have different, actual version of the software than you. If I think I'm running, version 1, and you're running version 1, I want it to be the same version 1. I don't want to have the secret backdoored NSA copy just for me. And this problem comes up over and over again. So, how could you go implement this? Well, here's just a cut and paste from something that I threw together. Not fully, but here's some Rust source code. And that's a transaction ID. Well, of course, in Bitcoin, a transaction can only be spent once. If it can be spent twice, Bitcoin doesn't work. Thus, we can use Bitcoin as a single-use seal. we can say our seal is a given transaction ID, and a given output number, more commonly referred to as an out point. We can throw together some code, go serialize, and so on. But the important thing is this means our witness is the transaction spending it and a block height. And if you go a little more fancy, you might say have an SPV proof, say the transaction really exists, right? But ultimately, this is fairly simple. And you validate it. Here's one possible way. But the important thing is, you just come up with some scheme. You say, well, you spend that out point, you have an output associated with it, and you do an operator and you commit to the message. You come up with a ton of variations on this. And then that would mean our blockchain looks like, well, what's the target? What's the chain? What's in the chain? Have a link between them, just what's the next thing and what's a witness, and have something to go hold the whole chain. And because each additional block in that chain is committing to the next seal, we can go repeat this indefinitely. All very simple. But, you do have this problem of scalability. Any of these things where you're just reusing Bitcoin transactions, it's like colored coins. Every state change in the system, every seal that's closed is one Bitcoin transaction. Question is, can we do better? And a thing to think about is, well, for Bitcoin itself, do you actually need blocks to be verified by miners? What if we just agreed on what's in blocks and we just reran the consensus algorithm ourselves? And provided you run the same algorithm as me, we can come to the same consensus. This is a realization I had a couple years ago. And my proposal for single-use seals is actually along the same lines. Imagine if we had some kind of publication layer. For convenience, we'll say it's divided into blocks. And we make a new definition of a seal, which is a seal is simply a pub key in an initial block. And for verification, well, we just take subsequent blocks and we run checksig on them. Each block commits to a message. That message we can interpret as a signature. And if the signature passes, now we say that that is a valid signature, and thus the seal is closed. And the first signature that's valid is the one that is the thing that's closed over. So then the trick there is, well, how do you agree on what the blockchain actually is, right? Well, we can create a blockchain with a bunch of single-use seals. Now we have a two-layer system. You can imagine taking Bitcoin and setting up a sub-blockchain of this proof of publication ledger, and every Bitcoin transaction that you spend commits to the next block in that ledger. Now all that data is off the chain. It's not on Bitcoin itself. Thus anyone with just a copy of the Bitcoin chain can't see that data. And this potentially scales. We can imagine, well, why don't we go and check against multiple messages in this block, and the first one that's valid is the one that wins. All well and good. Of course, this leads to an obvious question. Can we improve on this even more? Imagine if we had a couple billion of these seals, maybe every single one holding the state of every single property, parcel in the US, right? You might want to track who owns what property. Well, that's going to be a lot of seals. So the obvious thing to do is, well, we just index them. All right? Now remember, with a Merkle tree, you can go and take a whole bunch of different data and hash it together, but you can also create an indexed Merkle tree, which is the Merkleized equivalent of, say, a binary tree or something. What that means is, well, we have a key, and we can say, given this tip of this tree, give me the message it's associated with. Because everything's hashed, again, if we agree on the tip, you and I will come to the same conclusion. But the interesting thing here is, suppose I have a seal, and then you have a different seal. We do not need the same data to come to that conclusion for our different seals. I don't care whether or not your seal is closed or not. I only need the part of the tree that refers to my seal. Essentially this is like client or SPV proofs, where we take a Merkle tree and we extract a path, just one path up it. Same concept here. We can take a Merkle tree with potentially billions of items in it, and we can extract one path for every potential seal. So in practice, this might mean, my seal starts with bit 1 and et cetera, your seal starts with bit 0. In our Merkle path, right at the top they'll diverge, and we're having completely different data to prove our same seals. And then finally, well, let's go do the math. How does this scale? Well, for this type of scheme, first of all, we need to go prove that each block, we need the transaction outputs for each block. So you can imagine there's, about 1,200 bytes for the SPV proof that the transaction output's real, plus the transaction itself. If we're talking about something where, say 4 billion items are being, 4 billion seals are being closed every update in this block, we've got like 32 levels, 32 bytes a level for a hash. And then at the end of it, you'll run into a signature, right? And that signature is whoever happened to be publishing for that thing. And you can apply some improvements here, but we'll take an easy worst case, and that adds up to be about 3 kilobytes per non-inclusion proof, right? We're saying when this block was created, a valid signature for my seal's pub key was not published. We have to go show that, and we have to prove that that bit of data, is what was committed to, and that winds up being about 3K. Now in a real world system, you might have say 12 blocks a day, which is like every 2 hours, 3K block. Now this means if I want to prove to you the state of a seal, the rate at which that data grows is about 13 megabytes per seal per year. Well, let's go ask ourselves, is this practical? The simple answer is yeah, why not? There's plenty of websites out there that are already more than 13 megs. So say in my property titles example, that would mean if I have a house and I want to convince you that I did in fact own the house, and now I've sold the house to you and I've done a proper title transfer, I now have to give you 13 megabytes of data per year I've had that house. And per year, anyone prior to that has had that house. Or say I'm doing some kind of token thing where, a token represents maybe a bar of gold in someone's bank vault, or a US dollar in Tether's certainly existing bank accounts. Again, I can convince you this is true by giving you that data that shows that that seal is valid. But it's only a subset of the total data, thus the system does scale. Of course, we can go ask the final question is, well, hang on, what's the trust model here? And let's go back to our definition of a proof publication seal. Verify takes all that data and returns true under that circumstance. Well, what if you don't have the data? What if you have used a ledger that is now out of operation, or refuses to give you that data? Well, the simple reality is that's a censorship risk. If you don't have the data to prove to me that you own that house, you can't convince me of it. And to convince me that, you need that data. If the ledger doesn't give it to you, you're screwed. On the other hand, we can ask the opposite question, which is, can the ledger lie about who owns what seal? Well, they don't have the private key. They can't fake a signature. Bitcoin prevents them from creating multiple different ledgers because a Bitcoin transaction output can be only spent once. Thus, they can censor you, but what they cannot do is lie about the state of the ledger. So it's partly trustless. The other thing, of course, you can go do is, well, you can imagine a system where, suppose you don't like a given ledger operator. You could go close your seal over a message, then the context of the protocol means, hey, switch ledgers. Switch to, say, your own Bitcoin output, or ledger run by someone else. So you do flexibility. And again, once you've done this, you have the data to prove the status of that token, of that set of seals, without the involvement of the ledger. They're not saying anything. You have that data. You no longer have to go trust them. And finally, an obvious improvement is to go and just use a M of M scheme. If you have 3 ledgers and you say publish in 2 of them, well, if one goes down, that's not a problem. You've published in 2, and there's no way for you to fake it because it's majority. So that's one obvious way to get around this. If I had more time, I'd mention one more that we just came up with, but you can go look at my Twitter account to go find the discussion about that. It may offer a solution to the censorship issue. So finally, thank you. Questions?
So in the case of proving that you did not spend in a certain block in your single-use seal scheme, the obvious problem is censorship of just not giving the data to the person to be able to include in that 13 megabytes that they owe someone that they're proven to. So how do you, in the case of no malicious actor being involved here, what exactly are you getting from who? From which miners? Or from what ledger operator, and how do you get that? And if you're offline, what is the scheme involved for getting that data?
Well, I mean, if you're offline, you can't get it until you're online again. In fact, actually, come think it. I did skip through one seal. Why isn't, one slide? Why isn't this implemented yet? And that's part of the answer there, which is to make this happen, you do need a lot of work in actual software, writing protocols and so on to go do this sort of communication. An example being, I now need a wallet that can ask the question, all right, I have an incomplete seal proof up to this date. What data do I need to get from the people running that ledger? And you might start up your wallet and it will say, all right, I'll go download the last, 5 megabytes worth of data now that I haven't a chance to do so.
So you're relying on them to create non-inclusion proofs for you and then to give those proofs to you.
Absolutely you are. There's a potentially clever way to avoid this, which I haven't fully vetted, but this is fundamentally, from the point of censorship, a trusted system. Untrusted from the point of falsifying a proof, but absolutely trusted from the point of censorship. On the other hand, when we're talking about, say, a gold bar token or a house, you're already at risk of that. The government can just unilaterally say, well, that's no longer your house, we confiscated it, or we're just not going to give you that gold bar in the vault no matter what. So I think under that, for these types of systems, this is an acceptable trade-off. Similarly, you might do the trade-off saying, well, I personally own a bunch of property and a bunch of gold bars. I will run my own ledger, thus saving on Bitcoin transaction fees compared to a naive colored coin approach. Well, I'm amortizing all my actions for this one set of transactions. It's just not as cheap as, say, if I just trust, someone doing billions of these at once.
So first off, I'd like to say that I'm not a developer, so maybe this is going to be something not very precise, but from a very naive intuition, I just want to know from you if you've thought or if you've done any comparison. To me, as I said, very naive, it looks like similar to what some DAG-based coins are trying to do, without blocks, without miners, like the IOTA's Tangle. Have you done a comparison between the two systems, or?
Well, so I'd say the key thing I think you're missing is that I'm building a system that makes the assumption that you have a way of avoiding double spends in the first place. I'm assuming you have, say, Bitcoin or something like that can prevent a double spend, can prevent a seal from being closed twice. And once I have that primitive, well, then I can bootstrap on it. I can build a bigger system that's built on, say, Bitcoin, that provides these guarantees in a more scalable way. But without that base layer, I can't really provide any useful guarantees. Now, it's true that an actual implementation of this might say use a DAG or some other data structure, who knows. But that's really how you decide to use this basic construct, not the nature of the construct itself. Good, maybe we're back on schedule.